Good morning, everyone. I am John Leonard Marbelius, BAC, third year student. I am going to discuss about the boundary value problem. Ordinary differential equations involve one or more ordinary derivatives of unknown functions with respect to one independent variable. What we see in the picture, ordinary derivatives, v is a function of one independent variable. Unlike in partial derivatives, v is a function of one or more dependent variable. Ordinary differential equations involve one or more ordinary derivatives of unknown function. Boundary value problem is a system of ordinary differential equation with solution and derivatives values specified at more than one point. The solution and derivatives are specified at two joints, defining a two-point boundary value problem. A boundary value problem for a given differential equation consists of finding a solution of a given differential equation subject to a given set of boundary conditions. The auxiliary conditions are not at one point of the independent variable, and it's more difficult to solve than initial value problem. Initial value problem. A differential equation that has given conditions allows us to find the specific functions that satisfy a given differential equation rather than a family of functions. Boundary value problem and initial value problem. What is the difference? Initial value problem that has one point of independent variable or the same independent variable, while the boundary value problem more difficult to solve than initial value problem because the auxiliary conditions are not at one point of the independent variable.
There are two methods in solving for the boundary value: the shooting method and the finite-difference method, which will be discussed later on.
Good day, everyone. I will talk about the meaning and the usage of a shooting method. So what is a shooting method? A shooting method is a method for solving initial and boundary value problems for ordinary differential equations. It consists of introducing control variables and subsequently determining them from the system of equations where this choice of parameters has a decisive influence on the acceleration of the solution of the systems. So the term shooting method has its origin in artillery. When firing a cannon toward a target, the first shot is fired in the general direction of the target. If the cannonball hits too far to the right, the cannon is pointed a little to the left for the second shot, and vice versa. This way, the cannonballs will hit ever closer to the target. So, this method is based on converting the boundary value problem into an equivalent initial value problem. A trial and error approach is then implemented to solve the initial value version. So basically, a shooting method in a numerical analysis is a method for solving a boundary value problems by reducing it to the system of an initial value problem. Roughly speaking, we shoot out trajectories in a different direction until we will find a trajectory that has the desired boundary value. So here we have an example of a multiple shooting method applied. So the next one is a non-linear two-point problems. Linear interpolation or extrapolation through two solution points will not necessarily result in an accurate estimate of the required boundary condition to attain an exact solution. An alternative is to perform three applications of the shooting method and use quadratic shooting polynomial to estimate the proper boundary condition. However, it is unlikely that such an approach would yield the exact answer, and the additional iteration would be necessary to obtain the solution. So here we have an example of a non-linear two-point problems. The shooting method can become arduous for higher order equation where necessity to assume two or more conditions make the approach somewhat more difficult. Basically, kaning two-point boundary value problems are problems in which for a set of a nonlinear ordinary differential equations, some boundary conditions are specified at the initial value of independent variable, while the remainder of a boundary condition are specified at the terminal value of an independent variable. So kaning boundary conditions are therefore split between 2 points, the initial and the terminal value.
Hello everyone, I am Mega Ginger Ann Suarez, and today I will discuss to you the topic about shooting method. So, shooting method is one of the methods that we use in order for us to solve boundary value problems. Now, shooting method is based on converting the boundary value problem into an equivalent initial value problem. So the question here is, how does a shooting method works? Now, let's suppose we have a differential equation like this. So d squared y over dx squared is equal to the function of x, y, dy over dx. And here we are given a condition at y sub a is equal to y sub a, and at y sub b is equal to y sub b. Now we are finding right here is that we are given two boundary conditions, and what is happening to y is at x is equal to a, and what is also happening to y at x is equal to b. Now what the shooting method does is that it basically uses the initial value of problem methods. So initial value of problem methods. So we do have a boundary value problem, but in this case, we will be going to use the initial value problem methods to solve the problem. So what that means is that if we have this second order differential equation right here, and we are using the initial value method, then we would need the condition which was given, and that is y sub a is equal to y sub a, and then we would also need the condition of y prime of a is equal to, let's call it capital Y sub a. Now, in order for us to solve this particular problem right here, we can be able to use the different problem methods such as the Euler's method, range cotta second order method, and range cotta fourth order method. And we will also use this boundary conditions and this initial value right here to be able to do that. Now, we must also remember that if we are using the initial value problem methods in solving this problem, we cannot directly say that, okay, I will use the Euler's method and then solve the problem. So we must remember that initial value problems for second order differential equations such as this one will require us to have the initial value of y at x equal to a, and also the initial slope at x equal to b. And that is the only way that we can be able to solve the problem. Now, what the shooting method does is that in here, we already know this condition at x is equal to a because that was already given to us. However, in this part, what we will going to do is that we will going to replace this condition by this condition. And we cannot also directly say that I will be going to replace this condition right here by this because I like it. So what we are doing is that we are replacing this condition right here by this condition because that's what the initial problem methods will require us to do. So now, we will going to use this as our initial value, and in this part, we will going to guess, meaning we will going to guess this value of this one right here. So in order for us to do that, we will go from A to B. So let's suppose that we have here at x equal to A and x is equal to B. And we are going to use our initial condition, which is y sub A is equal to y sub A, and y prime of A is equal to y sub A. And we are going to use that in order for us to find the value at some point here by using the different initial value problem methods. So in here, we are going to find the value of y in this particular point, the value of y in this particular point, and lastly, the value of y in this particular point. Then eventually, we will going to end up right here, which is at x is equal to b. And in here, we can get the value of y sub b by using some numerical methods with the initial value problem. But the value of y sub b here is not going to be the same as this number right here. So, the question is why? So, it is because there is no way for us to know that our use value or our guess value was appropriate or not. That is why it is called as shooting method, because we are shooting for and hoping that our answer for y sub b will turn out to be very close or exactly the same as our number right here. But that's not going to happen because in almost every case, in this part right here, we are only guessing for the value of y sub b. And no matter how good we are at guessing and understanding the physics of the problem, this value of y sub b right here will not be exactly the same as this value of y sub b right here. So what happens is that once we obtain the value of y sub b by using the different initial value problem methods, the next thing that we must do is we must then again choose another value for y prime of a, and let's denote it as z sub a. So in here, we are choosing another value, meaning we have another initial guess, and through this, we will be able to get a different value of y sub b. And let's say in here, we get the value of p. On the other hand, for us to get the value of z sub a, we will follow the same procedure, and we will then again use this as our initial value of y and take the steps all the way up here, and by that we can get the value for z sub a, and we will denote that as the value of q. And that is how a shooting method works, and it is called as a shooting method because we are simply trying to guess the initial slope and hoping that the value of y, which are given by the other boundary, will turn out to be close to this number which is given to us. So sa Binisaya pa, shooting method is a method na kung asa magpili tag mga value sa atong slope, which is atong mga guess values, ug atong tan-awon if after pag-shoot nato sa bola is close ra ba siya sa atong target or dili. Then if layo ra siya sa atong target na value, then mag-adjust na po ta sa atong guess slope, Then balik na sad tag shoot to test if our second value is close na ba sa atong target or dili pa. So, if dili pa jud, we just keep repeating the process until makuha nato ang value na close sa atong y sub b. Therefore, shooting method is a method wherein mag-trial and error ta until makuha nato ang atong desired na mga values. So now we have here an example of shooting method. And in this, we'll be going to take a second order differential equation, but it's a boundary value problem. And in this, we will try to figure out how we can use the shooting method to be able to solve this particular problem. So for example, we have here d squared y over dx squared minus 2y is equal to 8x times 9 minus x. And we are given the boundary values at y sub 0 is equal to 0 and y sub 9 is equal to 0. So in here, we can say that we have two boundaries and that are x is equal to 0 and x is equal to 9. And the value of y here is 0 and the value of y here is also 0. Now, what we are asked to do is to simply find out what are the values of y at this point going from 0 to 9. And because we are trying to solve a problem through the aid of shooting method, we will then be asked to use some of the initial value problem method, which again are the Euler's method, the Runge-Kutta second order method, and the Runge-Kutta fourth order method. So in order to keep things simple, many people suggest that we should use the Euler's method because its formula is simple. So now, let's suppose that we are asked to use the Euler's method with a step size of h is equal to 3. Euler's method with a step size of h is equal to 3. So this h is equal to 3 means that if h is equal to 3, that means that one step will take us to x is equal to 3. The next step will then take us to x is equal to 6. And lastly, the final step will take us to x is equal to 9. So we are basically to conduct a 3 steps of Euler's method so that we can be able to get from x is equal to 0 and to x is equal to 9. And because we are solving this particular problem by the Euler's method, we cannot directly use these boundary conditions that were given. So for us to solve this problem by using the Euler's method, we need to know what would be the value of the derivative of y at x is equal to 0. So in here, we don't have a problem anymore of knowing the value of our y at x equal to 0 because that would still be the initial value that we will use in solving this problem. But since our value of the derivative of y is not given, then we will just assume it to be something. So in here, let's gonna assume that y prime 0 is equal to 4. So we assume that y prime 0 is equal to 4 and in conjunction with y sub 0 is equal to 0. Then we will going to use these two initial conditions to be able to solve the problem. So as I've said earlier, we are going to use y sub 0 is equal to 0 as our first initial value. Then we will going to assume that y prime 0 is equal to 4. And from this, we can now be able to get the value of y if x is equal to 9. So I have a question for you. Is it possible that we can get the value of y as 0 if our x is equal to 9? So, any guesses? So, the answer for that is we won't be able to get the exact value of 0, and we can only get the values that are close to the value of 0. And in order for us to do that, all that we need to do is that we will only then again change the value of this initial value of y prime 0, which we only assumed at the first place. So that is the whole point of solving this particular problem. So now let's go and see how we are going to go about doing that. So the next thing that we must do is we must write down this equation, and that would be d squared y over dx squared is equal to the function of x, y, dy over dx. And that would turn out to be equal to 2x plus 8x times 9 minus x. And also, since this is a second order differential equation, we already know that we can either use the different initial value methods such as the Euler's method, Runge-Kutta second order method, and the Runge-Kutta fourth order method. And all of this fall under the category that we can solve first order differential equations. So we have to reduce this second order differential equation, which is subjected to y sub 0 is equal to 0 and y prime 0 is equal to 4, which is an assumed condition. Therefore, from this, we can say that this equation must be reduced to simultaneous first order differential equations so that we can be able to solve it. So we can either say that dy over dx is equal to z. So we are going to assume that dy over dx is equal to z. So what that means is that we are introducing another variable, and that is z in here. So what that will do is that it will change this one to dz over dx is equal to 2y plus 8x times 9 minus x. So that's what it's going to get reduced to. So what that means is that this is the first function of x, which is the independent variable, and the two dependent variables, which are y and z. On the other hand, this will be a different function, which is the f sub 2, but still functions of the independent variable x and the two independent variables, which are still y and z. So this particular differential equation, which will be subjected to y sub 0 is equal to 0, which is right here. And this one will be subjected to z sub 0 is equal to dy over dx times 0, which is nothing but 4 itself. So that's how we set up these conditions, and now we got to apply this 1 and this 2. And now we will apply the Euler's method approximations on these two first order simultaneous differential equations. So let's see what those are. So from the first one, we will get is y sub I plus 1 is equal to y sub I plus the value of the function of f sub 1 and x sub I, y sub I, z sub I times h, where h is the step size. And in this case, here is it is the case number 2. And in this, we will get z sub I plus 1, which is equal to z sub I plus the value of the function of f sub 2, and that is x sub I, y sub I, and z sub I times h. So we have to use this step-by-step process because we will be able to know the initial values of x, y, and z, and we already know that what the step size is, and we know these individual functions, which is the f sub 1 and f sub 2. So from this, we will be able to calculate the value of y and z at a step ahead, and we will continue to do this until we reach x is equal to 9. So in here we can see that we have x is equal to 0, which corresponds to I is equal to 0, and then we will get to x is equal to 3, and that would be I is equal to 1 because it is the first step size, and we go to x is equal to 6, and that would be I is equal to 2, and lastly we then go to x is equal to 9, which would be I is equal to 3. So that is how the i's is going to work. So the next part of this video is the continuation of my discussion about how we can solve boundary value problems using the shooting method. So once again, I am Mega Ginger Ann Suarez. Thank you and God bless.
Hello everyone, before we start, let us first recall all the information we have gathered so far. Previously, we've managed to formulate these two functions. For our first function, we have here dy over dx is equal to z, where x is our independent variable, y is our dependent variable as well as z. And it is subjected for our first initial boundary condition, where y at 0 is equal to 0. For the second function, where x is our independent variable, y and z is our dependent variables, dz over dx is equal to 2y plus 8x multiplied by 9 minus x, and it is subjected to our first assumption of y prime at 0, which is 4. For this problem, we are going to use Euler method for the approximation. Since we have two equations or two functions, we will use two separate formulas for this equation. So we have for the first function or for the first equation, we have y sub 1 is equal to y sub 0 plus the first function multiplied by h. For the second equation, we have c sub 1 is equal to z sub 0 plus the second function multiplied by h. Now we have all the formulas and the functions. We can now proceed to our approximation. In I is equal to 0, we have these given values. X sub 0 is equal to 0, y sub 0 is equal to 0, c sub 0 is equal to 4, and h is equal to 3. If you are wondering where did we get this value of 4 for the c sub 0, c sub 0 or simply z is just equal to dy dx if you can observe this on the first equation. Z is equal to dy dx, right? And we all know dy over dx is just equal to y prime. And we all know that y prime is equivalent to 4, which is our assumption, right? So that means c sub 0 is also equal to y prime, which is just equal to 4. Now we have all the values or the given values. We can now substitute these values to our first equation or first formula. So for our first formula, substitute the values. We have y sub 1 is equal to 0 plus the first function multiplied by 3. Y sub 0 is 0, h is 3. For our first function, we have here dy over dx is equal to z, right? And we all know our first function is z. So this is nothing but z. And we all know z sub 0 is 4. So we only have 4 for the first function. So substitute the value 4. So we have y sub 1 is equal to 0 plus 4 for our first function multiplied by 3. And that will give us the value of y sub 1, which is 12. Now we done getting the y sub 1, we will now proceed to c sub 1. So for c sub 1, substitute the values. C sub 0 is 4 plus the second function multiplied by 3. For the second function, we have this equation 2y plus 8x multiplied by 9 minus x. We will now substitute the values. We have x sub 0 is 0, y sub 0 is 0, c sub 0 is 4. We will have 4 plus 2 times y, and we know y is equal to 0, so 2 times 0 plus 8 times x, or 8 times 0 because our x is 0, multiplied by 9 minus x, and x is 0, so 9 minus 0, and that will only give us a value of 0. So we have c sub 1 is equal to 4 plus the value of the second function, which is just 0, multiplied by 3, and that will give us a value of 4. Now we are done getting the value of y sub 1 and c sub 1. We will all compile everything. So we have here the value of y sub 1 is 12, c sub 1 is 4, and for x sub 1 is 3. Now to get x sub 1, you just need to add x sub 0, which is 0, plus the step size. Okay, so 0 plus 3 is 3. Then that's the value for our x sub 1. After solving for the values of y sub 1 and c sub 1, we will now continue in solving the values of y sub 2 and c sub 2. In order to solve for the values of y sub 2 and c sub 2, we will use the same formulas, but this time we will add one subscript into it, except for the functions. So for y sub 2, we have y sub 1 plus the first function multiplied by h, and we also have c sub 2 is equals to c sub 1 plus the second function multiplied by h. With that, we can continue our approximation. So when I is equals to 1, we have these given values. Again, x sub 1 is equals to x sub 0 plus h, which I have discussed earlier, and that is equals to 3. And we also have the value for y sub 1, which is equals to 12. C sub 1 is equals to 4, which we solved earlier. And the step size remain the same, which is 3. With that given values, we can now substitute the values into our formulas. So for y sub 2, we have y sub 1, which is 12, plus the first function multiplied by 3. As you can see, for our first function, we have only z. It only contains z. So we all know that the value of z is 4. We can just simply determine the first function. So our value for the first function is only 4. So 12 plus 4 times 3, that will give us the value of y sub 2, which is 24. After that, we will now solve for the c sub 2. So c sub 1 is 4 plus the second function multiplied by 3. Now we all know that the second function is 2y plus 8x multiplied by 9 minus x. So substitute with our values. We have here y sub 1 is 12, c sub 1 is 4, x sub 1 is 3. And then 2y is 2 times 12 plus 8x times 9 minus x, which is 8 times 3 multiplied by 9 minus 3, and that will give us 168. So 4 plus 168 multiplied by 3, that will give us 508 for our c sub 2. So we are done. So let's summarize everything. So for y sub 2, we have 24, c sub 2 is 508, and x sub 2 is 6. So how did we get that? So x sub 2 is equals to x sub 1 plus h, and we all know our x sub 1 is 3 and our h is 3. So add up together, that will give us 6 for our x sub 2. Before we start, let us first recall what is our main goal here. Our main goal here is to find out what is the value of y prime at 0 when the value of y at 9 is 0. We are using a shooting method with the help of Euler method for our approximation. Okay, now going back, we will use this formula in solving y sub 3. So y sub 2 plus the first function multiplied by h, that will give us y sub 3. Now let's begin. When I is equals to 2, we will have this given values. So for x sub 2, we will just add it. X sub 1 plus h is equals to 3 plus 3, and that will give you 6. Y sub 2 is 24, and C sub 2 is 508, which we have solved earlier. And H is 3. Okay? Now, substitute all the values to our formula. So, we will have Y sub 2, which is 24, plus the first function multiplied by 3. Now, again, our first function only contains Z. And we all know the value of Z is 508. And substitute, we will get 24 plus 508, which is the value of our first function multiplied by 3, and we will get 1548 for our y sub 3. And that concludes. So y sub 3 is 1548, and we all know y sub 3 is just equals to y at 9. So that means when the value of y prime at 0 is 4, the value of y at 9 is 1548. So as you can see, we did not get 0 at y at 9, which is supposed to be 0, right? Instead we get 1548. Now, this is our first guess, right? Our first guess give us 1548. Then our goal is to find out what is the value of y prime at 0 when the value of y at 9 is 0. Since it is 1548, that means we need to lower down our value. So we need to guess another number that is not more than 4. So it can be 3, but that's not recommended, because if it is 3, it is just still not closer to 0. So for me, I will just assume that the value of y prime at 0 should be negative 24. This is just my assumption. You can use any number, but make sure that it is not more than 4. Okay? So that will be my assumption. And then, since we already have this assumption, we will now proceed to our second guess. So for our second guess, we will just repeat what we did on our first guess. Again, we will have two equations. So for the first one, we have dy over dx is equals to z, and it will be our first function, where x is our independent variable, y and z is our dependent variables. And it will be subjected to our first boundary condition, which is y at 0 is equals to 0. So for the second equation, we have dz over dx is equals to 2y plus 8x multiplied by 9 minus x. And it will be our second function, where x is our independent variable, y and z is our dependent variables. And it will be subjected to our first new assumption rather, for the value of y prime at 0, which is negative 24. After that, we will now begin with our approximation. But this time, I will not show you the entire solution for the long process, because it will take us more time. Instead, I want you to solve this problem on your own so that you can practice. You can pause the video, and once you're done, you can unpause and compare your answers. You can, if you don't want to answer this problem, you can just continue watching. After solving, you will probably get this result. So with x sub 0, we have 0, y sub 0 is 0, c sub 0 is negative 24, x sub 1 is 3, y sub 1 is negative 72, c sub 1 is negative 24. X sub 2 is 6, y sub 2 is negative 144, c sub 2 is negative 24. For x sub 3, we have 9, and lastly, y sub 3, which is what we are looking for, negative 216. So, when the value of y prime at 0 is negative 24, the value of y at 9 is negative 216. So, in order to get the exact value of y prime at 0 when y at 9 is equals to 0, we will use this technique called interpolation. As you can see, we did not manage to guess the exact value of y prime at 0 when y at 9 at is equals to 0. So we will use interpolation technique. So we will compile everything. So y prime at 0, in the first column we have y prime at 0, and in the second column we have y sub 3, which is just equals to y at 9. So we have here 4, 1548, negative 24, negative 216, right? So we will use interpolation technique, but before that we will assign these values here on the table to another variable. So for the value of p naught, we will assign that to 4. For q naught, we will assign that to 1548. For p sub 1, we will assign that to negative 24, and for negative 216, it will be subjected to q sub 1. For the missing value or the unknown, we will assign it to p, and for 0, we will assign it to q. Now we are done assigning the values or the variables. We will now use this formula for the interpolation. So in getting the p, it is just equals to p sub 0 or p naught plus p sub 1 minus p sub 0 divided by q sub 1 minus q sub 0 multiplied by q minus q sub 0. So we have already assigned the values. We can now substitute the value to our formula. So by substituting, we can get this value to our formula. So 4 plus negative 24 minus 4 divided by negative 216 minus 1548 multiplied by 0 minus 1548. So using your calculator, you can get this value. So the value of p is negative 144 over 7, which is approximately equal to negative 20.57. So that means when y at 9 is 0, the value of y prime at 0 should be negative 144 over 7, or approximately equal to negative 20.7. So we solved the problem already. But there is a way of checking your solution. So instead of using y prime at 0 is equals to negative 24, y prime at 0 is equals to 4, we will use this value here, or the answer, to check if we get the correct answer. So in the next slide, I will show you how to check your answer. In order to check our answer if it is correct or not, we will just use the same process as what we did in our second guess on as well as on our first guess. So again, we will have two equations, dy over dx equals to z, and it will become our first function where x is our independent variable, y and z is our dependent variables, and it will be subjected to our first boundary condition, which is y at 0 is equals to 0. For the second equation, we have dz over dx. It will be equal to 2y plus 8x multiplied by 9 minus x, and it will be our second function where x is our independent variable, y and z is our dependent variables, and it will be subjected to our final answer, or our, let's say this is just our assumption, y prime at 0 is equals to negative 144 over 7. So we need to begin our approximation. So I will not just show you the long process or the long solution, so you will get this result. So as you can see in here, y sub 3, we ended up getting 0. So that means our answer is correct, because what we are looking for is what is the value of y prime at 0 when the value of y at 9 is 0. And as you can see in the table, the value of y at y sub 3 is 0. So that means our answer is correct. So that's all for this problem.
I am Mary Angel Mercader, BSc 3. I am going to report about the finite difference method. So what is finite difference method? It is the most common alternative to the shooting method, a class of numerical technique for solving differential equations by approximating derivatives. It converts ordinary differential equations ODE or partial differential equations PDE, which may be nonlinear, into a system of linear equations that can be solved by matrix algebra. Lastly, it is numerically more stable and converges faster than shooting method.
Another definition of finite difference method is it is used to solve boundary value ordinary differential equations. Because they are much easier to use, it replaces derivative in a differential equation with approximations, and the idea is to take those algebraic equations which are approximate to differential equations. It solves the resulting algebraic equations to get approximate solutions.
Accuracy and order of finite difference method. Error in a method solution is defined as the difference between the approximation and the exact analytical solution. Two sources of error in finite difference methods are round-off error, the loss of precision due to computer rounding of decimal quantities, and truncation error or discretization error, the difference between the exact solution of the original differential equation and the exact quantity assuming perfect arithmetic, assuming no round-off. To use a finite difference method to approximate the solution to a problem, one must first discretize the problem's domain. This is usually done by dividing the domain into a uniform grid. This means that finite difference methods produce sets of discrete numerical approximations to the derivative, often in a time-stepping manner. The quality and duration of simulated FDM solution depends on the discretization equation, selection and step sizes, or time and space steps. The data quality and simulation duration increases significantly with smaller step size. Therefore, a reasonable balance between data quality and simulation duration is necessary for practical usage. Large time steps are useful for increasing simulation speed in practice. However, time steps which are too large may create instabilities and affect the data quality. Example here is the heat equation in one dimension with homogeneous Dirichlet boundary conditions, where U sub t equals U sub xz, U 0t equals U1 t equals 0 or boundary condition. Then Ux0 equals U0 x initial condition. One way to numerically solve this equation is to approximate all the derivatives by the finite differences. We partition the domain space using a mesh of x sub 0 to x sub j, and time using a mesh t sub 01 to t sub n. We assume a uniform partition both in space and time, so the difference between two consecutive space points will be h, and between two consecutive time points will be k. The points will be u, x, j, t, n equals u raised to n sub j. Will represent the numerical approximation of u, open parentheses, x sub j, t sub n.
Hi everyone, my name is Gadis Jacob and I'm going to give one example of finite difference method. Example 1. The deflection of y in a simply supported beam with a uniform load Q and a tensile axial load T is given by d squared y over dx squared minus dy over ei equals qx times the quantity L minus x over 2ei, where x is the location along the beam in inches, T is the tension applied in pounds, E is the Young modulus of elasticity of the beam in psi, I is the second moment of area in inches raised to the power of 4, Q is the uniform loading intensity in pounds over inch, L is the length of beam in inch. Given T is equals to 7,200 pounds, Q is equals to 5,400 pounds over inch, L is equals to 75 inch, E is equals to 30 msi, and I is equals to 120 inch. Find the deflection of the beam at x is equals to 50 inch. Use a step size of x is equals to delta 25 inch and approximate the derivatives by central divided difference approximation to the solution, substituting the given values from this formula: d squared y over dx squared minus dy over ei equals qx times the quantity of L minus x over 2ei. So after nyo mag-substitute, mahimo na siyang d squared y over dx squared minus 7,200y over 30 times 10 raised to the power of 6 times 120 equals 5,400x times 75 minus x over 2 times 30 times 10 raised to the power of 6 times 120. So, after substitute, makakuha ta og answer nga d squared y over dx squared minus 2x 10 raised to the power of negative 6y equals 7.5 times 10 raised to the power of negative 7 times x times 75 minus x. So, input na nimo siya sa calcul nga mugawas na nga answer. Approximating the derivative d squared y over dx squared at node I, the central divided difference approximation. Illustration of finite different nodes using central divided difference method. D squared y over dx squared equals y sub I plus 1 minus 2y y sub I plus y sub I minus 1 over delta x squared. We can rewrite the equation as y sub I plus 1 minus 2y sub I plus y sub I minus 1 over delta x squared minus 2x times 10 raised to the power of negative 6 y sub I equals 7.5 times 10 raised to the power of 7 times x sub I times 75 minus x. Since delta x is equal to 25, we have 4 nodes as given in figure 3. So, anong nakakuha ta og 25? Since ang delta x kay nakalocate siya sa distance between 2 and 3, so delta x is equal to 75 over 3, so it is equal to 25. Node 2. Rewriting equation for node 2 gives y sub 3 minus 2y sub 2 plus y sub 1 over 25 squared minus 2x times 10 raised to the power of negative 6 times 1y sub 2 equals 7.5 times 10 raised to the power of negative 7 times x sub 2 times the quantity of 75 minus x sub 2. So, after ana, Makakuha ta og 0.0016 y sub 1 minus 0.00302 y sub 2 plus 0.0016 y sub 3 equals 7.5 times 10 raised to the power of negative 7 times 25 times the quantity of 75 minus 25. So, ang kanang 0.0016 y sub 1, gikan na siya sa kuan y sub 1 over 25 squared. So, input na siya sa inyong calcu, magawas na. Same goes with 0.003202 y sub 2. So, i-input na mo sa inyong calcu ang negative 2y sub 2 over 25 squared, and then ang 0.0016 y sub 3 kay ang y sub 3 divide sa 25 squared. So, after ang kanina sang pikas sa equal sign, mo atong input sa calculus. So, ang 7.5 times 10 raised to the power of negative 7 times 25 times 75 minus 25 kay ang result kay 9.37 times 10 raised to the power of negative 4. Node 3, writing equation for node 3 gives y sub 3 minus 2y sub 2 plus y sub 1 over 25 squared minus 2x times 10 raised to the power of negative 6. Y sub 3 equals 7.5 times 10 times I raised to the power of negative 7 times x sub 3 times the quantity of 75 minus 50. So, makakuha na sa pagtag 0.0016 y sub squared minus 0.0032 y sub 3 plus 0.0016 y sub 4 equals 7.5 times 10 raised to the power negative 7 times 50 times 75 minus 50. So, same man siya sa pagkuha sa node 2. Next, node 4. From the simply supported boundary condition at x is equal to 75, we obtain y sub 4 is equals to 0. Four simultaneous equations with four unknowns and can be written in matrix form as this. So, ato na siyang gi-input diha. So, kanatong gi-input diha, gikan na dito sa equation nga atong gi-solve from node 1, 2, 3, and 4. Next is, in solving the equations, we get this. So, para makakuha taan ni ang katong given nga equation sa natong gi-write sa matrix kay kuan lang mode 5-1. Then since ang y1 o ang y4 kay di ba 0 naman na nakabutang diadaan, so automatic po dire 0 na nang pud siya. So, y times 50 is equals to y times I sub 2 equals y sub 2 equals negative 0.5852 inches. The exact solution of the ordinary differential equation is derived as follows. The homogeneous part of the solution is given by solving the characteristic equation. M squared minus 2x times 10 raised to the power negative 6 is equals to 0. M is equals to plus minus 0.0014142. So, diin matagi kan aning plus minus 0.0014142. So, ang negative 2x times 10 times 10 raised to the power of negative 6 kaya transpose siya. Then, ang m squared kay, di-square root sila both sides para sa m squared makancel ang 2. Then, pag square root sa negative 2 times 10 raised to the power of negative 6 kay makakuha ta plus minus 0.0014142. Therefore, y sub h is equals to k1 e raised to the power of 0.0014142x plus k2 e raised to the power of negative 0.14142x. So, kani nga formula kay familiar siguro gikan sa pag-differential equation nato before. The particular part of the solution is given by y sub p is equals to ax squared plus bx plus c. Substituting the differential equation gives p squared y sub p over dx squared minus 2x times 10 raised to the power of negative 2. Y sub p equals 7.5 times 10 raised to the power of negative 7 x times the quantity of 75 minus x. So, next is substitute na nato ang value sa y sub p. So, mahimo na siya ang b squared over dx squared times ax squared plus bx plus c minus 2x times 10 raised to the power of negative 6 times ax squared plus bx plus c is equals to 7.5 times 10 raised to the power of 7 times x times the quantity of 75 minus x. Since b squared man siya, so mag-derive ta og kaduha. So, ang first derivation nato is 2ax plus b. Then, sa second derivation, kay mahimo na siyang 2a na lang. So, mo niya nakabutang diri kay 2a minus 2x times 10 raised to the power of negative 6 times ax squared plus bx plus c equals 7.5 times 10 raised to the power of negative 7 times x times the quantity of 75 minus x. So, after ani kay kani nasa gawas, ato na siyang i-distribute sa parentheses sa tagsa. So, first kay negative 2x times 10 raised to the power of negative 6 ax squared minus 2x times 10 raised to the power of negative 6 times bx plus 2a minus 2x times 10 raised to the power of 6 and c is equals to 5.25 times 10 raised to the power of negative 5 times x minus 7.5 times 10 raised to the power of negative 7 x squared. Yan, kanang 5.625 times 10 raised to the power of negative 5 x kay nakuha na siya kay g times ang 7.5 times 10 raised to the power of negative 7x sa 75. Yan, ang kanang negative 7.5 times 10 raised to the power negative 7 x squared kay i-times po na ang 7.5 times 10 raised to the power negative 7 sa x. So, mo na siya na x squared na siya. Gives negative 2 times 10 raised to the power of negative 6a is equals to negative 7.5 times 10 raised to the power of negative 7. Sa dili na part is kanang gina-partner lang sila kung kinsa nila ang nari kanang common. So, next is negative 2 times 10 raised to the power of negative 6b equals 5.625 times 10 raised to the power of negative 5. Then, 2a minus 2 times 10 raised to the power of negative 6c is equals to 0. Since wala may ka-common si c sa pika, so gi-equals na siya to 0. Solve the above equation gives a is equals to 0.375, b is equals to negative 28.125, c is equals to 3.75 times 10 raised to the power of 5. So, para makuha to para ma-solve tong equation na sa babaw, imo ra siyang i-shift solve then makakuha ta na nga answer. The particular solution then is y sub p is equals to 0.375 x squared minus 28.125x plus 3.75 times 10 raised to the power of 5. The complete solution is then given by y is equals to 0.375 x squared minus 28.125x plus 3.75 times 10 raised to the power of 5 plus k sub I e raised to the power 0.0014142x plus k sub 2 e raised to the power of negative 0.00141442x. Applying the following boundary conditions. So, mo niya itong mga boundary conditions. We obtain the following system of equations. K sub 1 plus k sub 2 is equals to 3.75 times 10 raised to the power of 5. 1.119 k sub 1 plus 0.8993 k sub 2 is equals to negative 3.75 times 10 raised to the power of 5. These equations are represented in matrix form by so, mo na siya kato na ang gi-input ang katong mga nakuha na or mga na-form na equation. A number of different numerical methods may be utilized to solve the system of equations such as ligation and elimination. Using any of these methods yields so after to nato makuha ang katong nasa matrix form kay kuha na to siya mode 5.1 then after makakuha ta og kanang result nga k sub 1 is equals to negative 1.77 5656226 times 10 raised to the power of 5. Then k sub 2 is equals to negative 1.974343774 times 10 raised to the power of 5. Substituting these values back into the equation gives y is equals to 0.375x squared minus 28.125x plus 3.75 times 10 raised to the power of 5 minus, so, substitute na ang value sa K1 which is negative 1.77565666 times 10 raised to the power of 5 e raised to the power of 0.0014142x minus ang K sub 2 which is negative or minus 1.9743437774 times 10 raised to the power of 5 e raised to the power of negative 0.00141442x. So that's the end of the example 1. Next is the example 2, which will be discussed by the next reporter.
Good day, my name is Florence Marie Intas, and to further understand our topic, I'm going to give a simple example. So example number 2, approximate the solution of the initial value problem y second derivative minus 1 minus x over 5 times y is equals to x, where the given boundary values or the boundary condition is y1 is equals to 2 and y3 is equals to negative 1 on the interval 1 less than or equals to x, x less than or equals to 3. Use 5 nodes to do the problem. So in this circle, so kani mga circles is known as nodes. So in the problem, since ang gihatag na number of nodes na gamiton is 5, we have in here 5 nodes. So to find the distance of each nodes, we have delta x is equals to 3 minus 1 over 4 equals to 0.5.
So kaning 4, it is the number of equal segment of the 5 nodes. So kaning 4 na arrow, ano siya. So that mean the particular distance between each node is 0.5 units. So ato na siya i-plus 1 plus 0.5 mo na siya na yung 1.5 plus 0.5, 2 plus 0.5, 2.5 plus 0.5 mo na 3. So we have to remember that the equivalent of y second derivative is equals to y sub I plus 1 minus 2 sub I plus y sub I minus 1 over delta x squared. Then the equivalent of y derivative is equals to y sub I plus 1 minus y sub I minus 1 over 2 delta x. In the problem, ang gihatag na equation is y second derivative minus 1 minus x over 5 times y is equals to x. So ato i-substitute ang equivalent sa y second derivative. So we have y sub I plus 1 minus 2y sub I plus y sub I minus 1 over delta x squared minus 1 minus x sub I over 5 times y sub I is equals to x sub I. So the next thing na atong buhaton is ato i-combine like terms. So we have y sub I minus 1 minus 2 plus 1 minus x sub I over 5 times delta x squared times y sub I plus y sub I plus 1 is equals to x sub I times delta x squared. For I is equals to 1, ato i-substitute tanan I into 1. So we have y sub 1 minus 1 minus 2 plus 1 minus x sub 1 over 5 times 0.5 squared times y sub 1 plus y sub 1 plus 1 equals to x sub 1 times 0.5 squared. So we have y sub 0 minus 2 plus 1 minus 1.5 over 5 times 0.5 squared times y sub 1 plus y sub 2 equals to 1.5 times 0.5 squared. So in continuation, we have to take note that the value of y sub 0 is equals to 2. So we have 2 minus 2 plus 1 minus 1.5 over 5 times 0.5 over 2 times y sub 1 plus y sub 2 is equals to 1.5 times 0.5 squared. So ato na siya i-calculate. So we have negative 2.175 y sub 1 plus y sub 2 is equals to negative 1.625. For I is equals to 2. So pareha lang gyapon sa gibuhat sa I is equals to 1 ato i-substitute tanan I into 2. So we have y sub 2 minus 1 minus 2 plus 1 minus x sub 2 over 5 times 0.5 squared times y sub 2 plus y sub 2 plus 1 equals to x sub 2 times 0.5 squared. So y sub 1 minus 2 plus 1 minus 2 over 5 times 0.5 squared times y sub 2 plus y sub 3 is equals to 2 times 0.5 squared. So ato na siya i-calculate. We have y sub 1 minus 2.15 y sub 2 plus y sub 3 equals to 0.5. And lastly, we have the I is equals to 3. So, ato gihapon i-substitute tanan I into 3. So, we have y sub 3 minus 1 minus 2 plus 1 minus x sub 3 over 5 times 0.5 squared times y sub 3 plus y sub 3 plus 1 equals to x sub 3 times 0.5 squared. So, we have y sub 2 minus 2 plus 1 minus 2.5 over 5 times 0.5 squared y sub 3 plus y sub 4 is equals to 2.5 times 0.5 squared. So in continuation, so we have to take note na ang value sa y sub 4 is equals to negative 1. So we have y sub 2 minus 2 plus 1 minus 2.5 over 4. 2.5 over 5 times 0.5 squared times y cube. Y sub 3 plus negative 1 equals to 2.5 times 0.52. So, ato na i-calculate. So, mukam up taog result na y sub 2 minus 2.125 y sub 3 equals to 1.625. So, next, ato na siya ibutang sa matrix. So, for I is equals to 1, we have negative 2.175, 1, 0, since walay y sub 3. Walay value ang y sub 3. Then, negative 1.625. The next, we have the I is equals to 2. We have 1, negative 2.15, then 1, and 0.5. And lastly, we have I is equals to 3. So, since wala tayo y sub 1, wala value yung y sub 1, so ato input is 0. Then, 1, then negative 2.125, and lastly, 1.625. And after that, makuha na nato ang atong answer, which is y sub 1 is equals to 0.5520, y sub 2 is equals to negative 0.4244, and y sub 3 is equals to negative 0.9644.
At this juncture, we are now at the part of conclusion. So to start off, as what we have known from the discussion before this topic was that an ordinary differential equation is accompanied by auxiliary conditions. So these conditions are used to evaluate the integration constants that result in the equation's solution. And equations are required for an nth order equation. So if all the conditions are specified at the same value as the independent variable, then obviously we are dealing with a problem with the initial value. So those discussion before has been dedicated to this type of problem. So in mathematics, in the field of differential equations, a boundary value problem is a differential equation together with a set of additional constraints which are called the boundary conditions. So I assume that you have know already what is boundary conditions specifically, which have been reported by my group mates from the beginning of this presentation. So moreover, a solution to a boundary value problem is a solution to the differential equation which also satisfies the boundary conditions. Now let us recall the boundary value problem. So when we say boundary value problem, it is a system of ordinary differential equations defined at more than one point with solutions and derivative values. So two joints that describe a two-point boundary value problem specify the solution and also the derivatives. So a boundary value problem for a given differential equation consists of finding a solution to a given set of boundary conditions for the given differential equations. So why is boundary value problem important? So maybe we have asked that when we have learned what is boundary value problem from the previous slides of this presentation. So boundary value problems are extremely important as they model a vast amount of phenomena and applications. So specifically from solid mechanics to heat transfer and also from fluid mechanics to acoustic diffusion. Next, it is also important because they arise naturally in every problem based on a differential equation to be solved in space, while initial value problems usually refer to problems to be solved in time. Now, as you have known, there were two methods of boundary value, specifically mentioning shooting method, and the second one is a finite difference method. But at this juncture, let me expound first the shooting method. So This approach applies to all sorts of boundary value questions. It is regardless of the shape of the boundary conditions. Difficulties may arise due to severe error propagation in the integration of the initial value problem, apart from the problem of obtaining good estimates to begin the iteration. So the missing conditions at both ends of the range are indeed a useful improvement to guess, matching the two solutions to defined at an interior point. Second, the shooting method works by considering the boundary conditions as a multivariate function of initial conditions at some point. So, before we proceed, when we say multivariate, it is having or involving a number of independent mathematical or statistical variables rather. So, it is reducing the boundary value problem to finding the initial conditions that give a root. So maybe in the beginning of this presentation of ours, you have asked yourself what is the significance of this particular method or the shooting method. So at this juncture, let me talk about the question is why we use shooting method. So the shooting method is a method of solving a boundary value problem in numerical analysis by reducing it to the system of an initial value problem. So we are aiming out trajectories in various directions, which is in generally speaking before we find a trajectory with the desired limit value. So next, the advantage of the shooting method is that it takes the advantage of the speed and adaptability of methods for initial value problems. On the other hand, I must say that the disadvantage of the method is that it is not as robust as finite difference method because some initial value problems with growing modes are inherently unstable, even though the boundary value problem itself may be quite well posed and stable. And now let's go to the second method of boundary value, which is the finite difference method. When we say finite difference method, it is a class of computational methods for solving differential equations in numerical analysis by approximating derivatives with finite differences. Both the spatial domain and the interval of time, if applicable, are divided into a finite number of steps, and the solution value is approximated at these discrete points by solving algebraic equations containing finite differences and nearby point values. So to make it simple and easy to understand or to remember, finite difference methods use discrete approximations to the space derivatives. So this results in a set of ordinary differential equations that can be solved numerically. So next we have the finite difference method is one of the oldest and one of the most reliable methods of solving specific problems such as electromagnetics problems. So the method is both rigorous and flexible, so it remains the method of choice for many classes of problems. The method is easily adaptable to problems. And next, I have mentioned that this method is used in solving electromagnetics problems. Therefore, this is really convenient. Equivalent circuits exist for a number of 2D and 3D problems. The method results in a simple and easy to program set of equations that are generally sparse, symmetric, and well behaved. Next, you may have asked while learning the finite difference method from the previous slides, what is the significance of such methods? So I am going to answer the question stating why we use finite difference method. So first, the finite difference method is an approximate method for solving partial differential equations. It has been used to solve a wide range of problems, and these include linear and nonlinear, time-independent, and dependent problems. Next, finite difference method can give a complete view of the problem so as to monitor the calculations. Moreover, it can treat different boundary and initial conditions flexibly. Next, an important advantage of the method of finite difference is because of its simplicity. It is not difficult as it involves only simple arithmetic when it comes in the derivation rather of the discrete equations and in writing the corresponding programs. Another advantage is the ability to obtain high-order approximations quickly and thus to achieve high-order spatial discretization accuracy. And next, this method can be applied to problems with different boundary shapes, different kinds of boundary conditions, and for a region containing a number of different materials. So, specific reference concerning the treatment of electric and magnetic field problems is made in. So for more information, during 1950s to 1970s, finite difference method was the most important numerical method used to solve practical problems. With the development of high-speed computers having large-scale storage capability, many numerical solution techniques appeared for solving partial differential equations. However, due to the ease of application of the finite difference method, it is still a valuable means of solving these problems. So, in conclusion, with these two methods, we cannot deny the fact that these are relevant to the numerical analysis in the study of algorithms that use numerical approximation for the problems of mathematical analysis. Moreover, as to boundary value problem, it should be well presented in order to be useful in applications, and this implies that there is a unique solution given the input to the problem, which continuously depends on the input, obviously. So, in addition, much theoretical work is dedicated to showing that boundary value concerns resulting from science and engineering applications are currently well positioned in the field of partial differential equations. So that's all for the conclusion, and I hope that you learned a lot since from the beginning of this presentation until the very end. So that's all, and thank you.